this session on masking, another session on masking. First of all, we have Felix Ule giving further evidence to not employ customized mask hardware, identifying and fixing flaws in SCARF. Yeah. Please go ahead.
Thank you for your introduction. Yeah, thank you for joining my presentation. I'm going to explain you which flaws we have identified in the RISCV core SCARF, or in the mask instruction set extension of this core, how we have found them, and how we have fixed them. Okay. So since this is a masking session, we have to start with a normal background. When we implement cryptographical algorithm, which are secure in a black box model, we face a problem of physical attacks, which targets implementation and not the algorithm. And one of these attacks is side channel analysis, which utilizes the dependency between the processed data and the physical effects caused by the processing of these data. And one solution to avoid this problem, to counteract this problem, is masking. And the basic idea of masking is to split the dependency between the processed data and its physical effects. This is done by sharing our data or splitting our data, our secret data, into multiple shares, which are statistically independent of each other. And one form of masking is Boolean masking. Here we use the XOR operation to split our secrets into the shares. Using masking, we can create or we can counteract side channel analysis, but we need some models to define the strengths of the implementation of our mask implementation. And one of these models is the deprobing model. In this model, the adversary knows the circuit, and he can select up to D positions he wants to probe. Here we have two probes, one on the output of the circuit, Q0, and one of these register. And probing here means that the adversary learns a stable value and the noise-free value. We have, here in this case, again, we have two probes, so D is equal to 2, and these are security parameters. So higher D means stronger adversaries. And we have security in this model if no combination of up to D shares reveals any information about the secret or the secrets. Here in this case, our secrets are A and B. In real hardware, we face the problem that our values are not perfectly stable. We have physical effects, such as glitches, which can reveal even more information. What is a glitch? So a glitch occurs by temporarily intermediate computations caused by the different computation time or propagation time of different signal paths. Besides that, besides that, it's allowed to extend our probes, to glitch extend our probes to the last register stage. So here in this case, the probe on Q0 is extended to register 0 and register 1. Or if there is no register in the computation path up to the primary inputs, we have no difference in the security definition. So here it's still the case that we have security when all combinations of up to these shares are statistically independent of our processed information. Okay, so. And we can use these models to prove our security. For smaller circuits, probably possible to do it by hand, right? So we have to prove for all combinations of up to the probes that there is no dependency between the secret and this combination of probes. But for larger circuits, we need some tools to do this for us. And one tool which can do it is ProLead. ProLead takes a netlist and computes many simulations on this netlist. This can be defined by the user how many you want. And then some statistical tests are performed. And based on the statistical tests, then we can follow if the netlist leaks for a security already, or if it is leaks free. And one circuit we can check using ProLead is the circuit we can see here. It's a domain-oriented masked AND operation in its dependent form, so we can have dependently shared inputs. And it's a reduced randomness form. So the difference to the normal one, the normal DOM-DEP is to the generic one is that we do need here only 2 bits of randomness instead of 3, which you would normally need for first order security. So yeah, this circuit is first order secure. And yeah, we can implement, normally we implement this in hardware, but we can also implement it in software. So for both strategies, we can protect against side channel analysis using masking. And the most prominent advantage of using hardware masking is that the security we can observe in practice is approximately the security we can derive in theory. We have area overhead since our chairs are processed in parallel, and normally hardware is unchangeable after manufacturing. So yeah, we have this disadvantage. For the software masking side, we can change our code. Yes, in the software we can just apply some updates, and instead of area overhead, we have latency overhead here, since our chairs are now processed sequentially instead of parallel. But the biggest disadvantage is that the security we can observe in practice is not necessarily equal to the security level we derive in theory. And the problem here is that our software is executed on some processor which has a microarchitecture, and this microarchitecture is not known to us, and there can happen some things like share recombination in the cache or something like that, which recombines our shares and causes leakage, and we have no control over this. And there are 3 approaches we can use to address this. And the first one is that we can adopt our assembly code as long as the execution of our assembly code on a specific platform contains leakage or leads to leakage. So we start by measuring our execution. When we find leakage, we adopt it, and we repeat this until there's no leakage anymore. So it's quite heuristic, and this approach tightly binds the code and the security to one execution platform. A more theoretical approach is to choose a conservative model, which captures even the worst behavior of the microarchitecture. This is really conservative, so it leads to huge overhead in our code. It slows it down. But there is a third approach which can combine the advantages of both sides, which is implementing a mask instruction set extension. Here we have the advantage that the theory is more or less, the security in theory is more or less the security in practice. We have still the area overhead, but we have changeability, since only our individual instructions are implemented in hardware, but the execution of code using these instructions is implemented in software. And one work which did this is a paper, an instruction set extension to support software-based masking by Gao et al., presented on CHES 2021. And this work features Boolean and arithmetic mask operation, as well as a few more, like converting between the both worlds. And the security of these mask instruction set extension was empirically evaluated on an FPGA board. There are no proofs of security of the individual module or the whole core. And we have repeated these measurements, and we found after only 450,000, 400,000 measurements leakage in both the ALU and the add operation. And then we decided to investigate the reason for that. So let's start with the AND operation. They've implemented it using these domain-oriented masking in the dependent form gadget. We have now seen multiple times, but they missed 2 critical registers, so register 0 and 3 were missing, and therefore we can extend our probe to Z0 and B0, which is a problem since register 1 contains Z0 XOR B1. Therefore, we can easily compute B, which is one of our secrets. And the easy fix here is to just add our missing register, or the missing registers. So we did this, merged it back to the whole core, and then we extracted the add module and simulated this module with ProLead. And we found leakage again. So ProLead found after only, I think, 9,000 simulation leakage. And the reason for this is the design of this iterative Cog-Stone adder. We have these, okay, I have no pointer, so it's hard to show. We have here iterative paths in the, between the DOM indep module, the shifter, and the multiplexer. So we have 6 iterations here on both sides, but we focus now on the left side. The reason for the leakage here is that the output of the DOM indep module are directly fed back into the input of this module, and there is no register stage between. And this allows us to access paths or combination of output bits of the previous iteration, which are not used for computation but accessible by glitches. And here we have an example. So when we are in the second cycle, we can access by glitches the computation of the first, or the inputs which are used for the first cycle computation by glitches. And when here I have visualized the probe, so we probe this TP1 register here and get access to the computation A0 and B0 and A1, C1. And when we plot the histogram of the joint distribution of these both probes, we can, condition on the value of A, we can easily see that we can distinguish A equal to 0 and A equal to 1. Therefore, we have leakage. And the reason to the countermeasure to mitigate this is, or we have 2 possibilities here. We can just add a register in the green parse or in the blue parse. We opt for adding registers to the green parse since it requires less changes to the control logic. When we zoom out, we can see that adding these registers in this iterative path, that we double the computation time, so huge overhead. But after this fix, we found no leakage anymore using ProLead. So we assume that this is secure now. Okay. Now, everything I have mentioned until now, all leakage I have mentioned now was caused by individual modules, flaws in individual modules. But there are also flaws caused by the composition of these modules. And what is the composition here? So we have ALU, and this ALU computes multiple instructions. We have one module for each instruction, and these modules are then, or the output of these modules are fed to a huge multiplexer, which decides, based on the opcode, which output should be forwarded to the output of the ALU. Therefore, when we place a probe of the output of this multiplexer, we get the outputs of each of these modules, and all of these modules are clocked. So in the case of the ALU we have investigated, there's no reset signal or something else which stops the modules from working. And in the following, I will explain, or I will give an example what can go wrong here and what went wrong actually by investigating the combination of the shift and the end module. ProLead also identified as a problem. We can see here again our end operation and our shifter, and the shifter is constructed by a multiplexer which selects conditioned on the last 5 bits of B0, which of the 32 possible shifts should be forwarded to the output Q0. By placing now a probe, on the output we get access to the last 5 bits of B0 and through the end module to B1, and therefore we can trivially compute the last 5 bits of B, which again is a reason for leakage. So how can we fix this? So the approach we choose here is to just add to the modules which contain no register already, a register in the end, which is resetted if the corresponding opcode is not chosen. We had also to change the registers in the already clocked modules to be resettable when the corresponding opcode is not chosen, to prevent another class from leakage. I'm not going into details here, but it has something to do with transitions. And all these changes I've shown now doubles the size and doubles the latency of the core we have now, but this core is secure. So ProLead found no leakage anymore. But we have another problem. Since I've already mentioned, this is a mask instruction set extension, so we have the normal instruction as well. So we have two ALUs side by side. And when we instantiate both of these ALUs in the whole SCARF core, we can still measure leakage on an empirical setup on an FPGA. And the reason for that is that the ALU and the mask ALU share one register file. There is a countermeasure, so the shared data is stored in the register file in bit reversed order, but it seems not to be enough to protect against leakage. So the easy fix here would be to just use two register files or to develop a more sophisticated countermeasure. And yeah, to now sum up what we did. So we have identified and fixed 8 floors. The top 3 row, or the 3 floors there in the top row are these I have explained now in details. There are some more. So for example, the randomness generator was not enough random, so ProLead found leakage when we used this random generator on our secure ALU. Randomness was reused in a fashion which leaks again. We have some problems when we have the same data, but we switch the opcode. Then it happens that some data are processed in a fashion that again leak. And we have some incompatibility between the different operations. So like, for example, the XOR is used as a pre-processing for the add operation, and this has introduced leakage as well. So we have fixed all these flaws, which were unnoticed due to the large and complex design of the ALU we have investigated, and they were unnoticed due to only empirically evaluate this large core. And all of these modules were custom masks, so there were no proofs of security or composability. And together, this provides another evidence to not employ customized mask hardware. Or if you require it, right, for performance reason or something like that, then you should do at least tool-assisted evaluation to avoid the strict connection between your measurement setup and the result if you find leakage or not. Yeah. Thank you.
Thank you. So, let's thank the speaker. So we have plenty of time for questions. So, okay, we have someone standing up.
Thanks for the very nice talk. It's very interesting to see how many bugs there can be, and you have found fixes for all of them, but are you confident that there are any more in there, or do you think we fixed all of them?
Sorry, could you repeat the last part?
Are you confident that you fixed all the bugs?
Yeah, it's a difficult question, right? Because I think everything we have tested with ProLead, right, and fixed then is fixed. So, but the problem is, again, what I have mentioned. You have different instructions, and we were not able to test all possible combinations of instructions computed sequentially. So when there is some problem between two sequential operations or something like that, we might not have found all of these leakage caused by such things. Yeah, there might be some further things probably it has not detected due to the low impact, right? Because the most expensive experiments we did took 2 terabyte of RAM and I think 2 days of computation. So quite expensive to do. Yeah, so no, I'm not 100% sure that we found everything, but my confidence is comparable high. Yeah, that we found everything we have investigated.
And maybe follow up if you have time. Did you try other formal verification tool that do not have this problem of probably that we use a lot of RAM and computation to maybe never hand?
So there was the idea to use Silver or Verica, right? But nothing more, right? We have a bit the problem that we need a clock cycle notion for this kind because we have this iterative construct in the adder, and this is not supported by Verica as far as I know. Yeah, and no, so we tried no other tools. Maybe we could, but yeah.
Okay, thank you.
So, okay, if I may. So, of course, there's gadgets that are composable. So I guess one could use just gadgets that have this property that you can compose them. Okay.
So yeah, it would be an idea, right? You probably get an overhead, but the question is now if the overhead you get by using these gadgets, if this is larger than the one we got by just empirically fixing the flaws.
Fair enough. And for the security testing, when you say secure, that you had like T-traces in there, so it's like first order T-testing, no horizontal attacks, nothing like that. It's a
Yes. So the empirical evaluation was a T-test and probably uses a G-test.
Okay. Now, thank you very much. Actually, I have, because the next speaker happened to be one of the authors of SCARF, I would be very curious to know his input on this. So, come on up. All right.
I'm sorry.
No, you fixed all the bugs. You made it perfect now, so it's good.
Yeah, that seems a bit mean. My views? What have you?
Well, I mean, what do you think?
So the first thing I would say, it's good that somebody took the work that existed. I think this is a good outcome that it was made open and available, because problems like this otherwise just sit behind closed doors and don't ever get examined. So I think that's a good thing. I'm not sure what else you want me to say. I mean, yeah, this is, you can't argue with facts, really. I think maybe. I think what maybe one thing that's missing is the gap between the concept and the implementation. So
yeah,
whether this is a good idea to do at all is a bit different from whether this particular implementation is good or bad. I think bad is the evidence, right?
Yeah.
May I give a comment here? I mean,
Please.
The paper was, your paper was 2020, right? 2020, yeah? And then at that time, the composable gadgets were not, with security guarantees were not existing. And then these tools that we have used also were not existing. Then that's something that could happen. I mean, and at that time, there was no easy way to find the problems, yeah? Then it's absolutely fine, yeah?
Yeah, all right. I consider this as scientific progress that is happening here, so that's thank you both. Now, also, I'd like to read out the names of the co-authors. So, of course, we had Felix, and then there's Florian Stolz, Amir Moradi commenting, I believe, and yes. So let's thank the speaker again. Now, the next talk is highly related to the previous one. So this is eliminate a leakage-focused ISA for mass implementation. So this is doing kind of the thing that the title of the previous talk says not to do, but we are still doing. So this is given by Daniel Page, co-authors Hao Cheng and Weijia Wang. So please.
So I'm not sure I necessarily agree that this is doing the same thing necessarily.
but I'm not sure. I'm stood on shaky ground already, so maybe I'll just get on with this and we'll see. So most of this work was done by Howe while he was visiting Bristol. It's a pity he's not here to take the credit for that, but he wasn't able to get a visa to attend. So the context is software-based masking or implementing masking in software. I think most people who've tried to do this would agree that it can be quite challenging, in particular because there's a whole raft of different pitfalls that you can get stung by. One of those pitfalls is the so-called overwriting effect. This is something that's been, instances of which have been identified and explored by lots of people now, maybe the first of which is the paper cited here by Papagiannopoulos and Veshikov. So in concept, this is relatively straightforward. You have to imagine that there's some storage resource, some register or something like this that exists. At some point in time, you write a value into this resource, and then at some point later, you write a different value. And of course, the second value overwrites the first one, and as a result of this transition, the leakage that you produce is some function of these values, so the Hamming distance between them, for instance. This is a session on masking. For sure, this is a big problem for masking, because as soon as these values are shares, then of course you start leaking information about the underlying value that's being masked. But actually, I think this is probably fair to say that this is a bit more general, in fact. This doesn't just apply to masked implementations. It can bite you in other ways as well. Anyway, you might look at something like this, and because it's relatively simple to explain, you just say, well, yeah, the answer to this is kind of easy, just don't do that. There's various different ways you can not do that, of course. One is that you can try to flush the resource before you make the second assignment. So you kind of pre-zero the register in this case, so that the second write is overwriting a 0 rather than the first value. The other way you can approach this is just you choose a different register allocation, potentially. So instead of writing into register X here, we write into register Y, and as long as you're confident that register Y hasn't got one of these values that it shouldn't be overwriting, then this can also save you. In reality, though, this is a little bit more challenging. One of the challenges, for sure, is the fact that when you start to look at implementations that become increasingly large and complex, actually identifying instances of this alone can be difficult, and then solving them likewise. Of course, automation like Rosita helps this to some extent, but I think this scaling complexity just in general makes this more difficult than it first seems. The second challenge is that you can't actually access all the resources that you might want to. So overwriting happens in architectural resources like the register file, but also microarchitectural resources that you don't have direct control over. This can be difficult, therefore, to solve the problem, at least in the same ways. And then finally, there's the issue of efficiency. Even if you find a solution that's secure, the actual overhead of doing this potentially is at least unattractive. It can build up. So you might say, well, okay, doing this in software, this isn't what I want to do, so maybe I try instead to task the hardware with helping me out to some extent, or maybe completely actually taking over and doing this for me. So actually have the microarchitecture avoid overwriting. Again, this has some challenges. I mean, it would be nice if this actually just worked, but for instance, the cost overhead of doing so could be prohibitive. This is a quote from a paper by Giegel and others. This is the work on the COCO toolset. Their claim is that fixing overwriting problems in hardware would, in principle, be possible, but it would be very costly. And actually, this quote is kind of our motivation, really. We wanted, I mean, it seems completely reasonable to say this for sure, but we wanted to explore in a bit more detail what that cost might look like and whether there were any trade-offs that you might be able to make so that the cost in one metric is offset by another. The other challenge is that the ISA, the instruction set, it sort of prevents the microarchitecture knowing actually that you're executing some masked implementation. So you end up in a situation potentially where you either have this either always on or always off, and I guess always off isn't going to really help too much, so always on is the only remaining option, and again the cost of having it always on is maybe not so great. So yeah, the natural sort of next step would be to ask whether there's a middle ground, and the natural middle ground would be some kind of combination of both of these approaches through an instruction set extension. When we wrote in the paper, this is a sort of an offshoot. We tried to categorize the different types of approaches by which you can assist a software-based masked implementation, or masked implementation full stop, I guess, because the far left-hand side is to do this purely in hardware, in fact. So there's a kind of a sliding scale from left to right, where you start with more hardware and end up with more software on the right-hand side. There's actually two middle points, two hybrid points here, and I think what I wanted to point out actually is that there are a bunch of different proposals for what you might call compute-oriented instruction set extensions for masking. These are things that provide you with some computational ability that's related to masking, right? It maybe execute some gadget or so in hardware for you. We saw an instance of this in the last talk. What we're doing isn't that. What we're doing, we've called data-oriented in the sense that it's not giving you any extra computational ability. It's simply signaling to the microarchitecture that what we're doing here is masking, and actually you should be aware of that and take appropriate action. So this is why I said it's not really the same thing. Okay, so what does this look like in practice? I think it's fair to say what we're doing here is actually pretty simple. The base ISA that we're using is 32-bit RISC-V, but there's nothing per se that prevents you applying a sort of similar technique to other instruction sets. So what we do is provide two classes of extra instructions, one of which is computationally related and one of which is storage related, so basically loads and stores. Both of these sets of things essentially have the same semantics as the existing sort of insecure versions, if you like, the kind of vanilla versions, except for the fact that we have this extra hint that is communicated as a result of using these variants. So by using the secure XOR instruction, essentially you still have the semantics that say take two operands and XOR them together to produce the result, except that you're kind of also communicating you should avoid the overwriting effect whilst you're executing this thing. I think a little bit of a challenge, maybe I'll come back to it later if I have time, is to sort of express that hint in a way that's constraining enough that it's useful, so it provides a guarantee to the software developer that's actually useful and that they can leverage to write better, more secure software, but it's not over-constraining such that you simply can't realize it in the microarchitecture. So finding a balance between these two things is a kind of somewhat delicate one. You know, I think if you were to extend this type of approach to other forms of microarchitectural leakage, then that becomes more and more difficult. But we're very strictly considering overwriting-based leakage alone here, which is, I guess, you sort of view this as necessary but not sufficient to eliminate all leakage, of course. So we have these two classes of instruction that are added to the instruction sets. The extra hint that that they provide sort of is some kind of contract, I guess, then between the hardware and the software. We consider two different implementations of the instruction set extension itself, both of which are based on use of vanilla IBEX as the base call. The two different implementations are essentially there to explore a trade-off between latency and area, because, like I say, the actual definition of the instructions doesn't really say how you should avoid the overwriting effect. It just says you should do this. So we have two variants. Like I say, one is latency optimized and one is area optimized. Actually, if I describe the area optimized one first, I think this is extremely straightforward. The idea here is that both classes of instruction are executed by taking a kind of double-step approach. So double-step in the sense that the first step will try to pre-zero or flush the resource that might be overwritten and cause us problems. And then the second step is essentially just the normal step. So yeah, I would sort of frame this as kind of analogous to where you have a logic style that has a pre-charge and an evaluate phase, perhaps. Or the other way to look at it is that we're basically just doing in hardware what you might write in software, but we're kind of wrapping up both of those instructions into one. The latency optimized implementation is considerably more involved. The goal here is to really avoid what is obviously a pretty high overhead in terms of latency if you take the second approach. You know, you're essentially doubling the latency of everything. The way we do this is to deal with the class 1 instructions by essentially taking a double buffer style approach. I would describe this as basically using sort of spatial redundancy in contrast to implementation number 2, which is sort of doing temporal redundancy. The class 2 instructions are more difficult to cater for. These are accessing memory, if you remember. The way we address this is by using kind of an existing design that was developed by, who was this? De Mulder and Hutter, and I forget the third author, Rambus. The idea basically is to remask the value that's being written or read at egress or ingress to the actual core. So as it's being written out to the memory, we remask it, and when it's being read in, back in, we sort of reverse that process. It's important to say that both of the implementations take a pretty conservative approach to anything that's outside the core. So of course you could couple your core to any kind of bus or memory potentially. Some of these things would have resources in them that we can't predict or know about or control. So we take a conservative approach and assume that they're there, which kind of means that we take a hit in terms of any sort of performance metric, but we're kind of more robust as a result, I guess. The second thing to be clear about is that our latency optimized implementation, the class 2 instructions depend on some state, in particular some control and status registers, and I'll sort of explain what that means in a second. Okay, so I wanted to kind of just really show you some pictures of how implementation number 1 looks like. The example here is an XOR, but essentially it doesn't matter so much. Within the core, there's sort of 2 different types of resource that we try to deal with. One is a sort of an isolated register of some sorts, and we deal with that using a gadget, essentially, that looks somewhat like the diagram here. So we start off on the left-hand side with a single register. We essentially duplicate this register and make sure that in any particular clock cycle, we're zeroing one of those things and writing into the other one, and then we sort of flip back the other way around in the next clock cycle. So then you're overwriting the 0 that you wrote in the previous clock cycle. This works pretty okay for isolated registers, but when you consider the register file, duplicating this entirely is pretty expensive. So we take a sort of slightly different approach for the register file and employ what you could describe as a kind of lightweight register renaming strategy. The idea here is that we have a physical register file that's 1 register bigger than we need. One of the registers is used as an idle register, and again, we're always writing a 0 into this thing, and we're updating the mapping between the logical and the physical registers to make sure that everything is consistent. So we can always write into a register that's was written 0 in the previous clock cycle. The class 2 instructions, like I say, operate by masking or unmasking values that are written to or read from memory. The way this works is in the diagram here. It's essentially replicating the design that is referenced in the slide. The idea essentially is that along the top path is your data value that's being XORed with something that's produced by the PRG in the sort of middle of the slides. And the PRG is essentially dependent on, number 1, the address that you're making use of, and number 2, these so-called seeds that are stored in our CSRs. So the long and the short of it is, as long as the programmer correctly controls the value of these seed registers, then they're able to make sure that the values being written into the memory are sort of independent from whatever the masking scheme is using, and make sure, sort of ensure that the overwriting effect is eliminated therefore. The crucial thing here, of course, is that there's a big if there. If the programmer can make use of these effectively, whereas with our class 1 instructions, you pretty much get this for free if you're the programmer. All the hard work is done by the hardware engineer. With this specifically, you have to work a bit harder. There's a usability issue, you could say. I am somewhat now terrified to talk about evaluation, but I'm going to do it anyway. So we evaluated this in 2 ways. The first was an empirical evaluation. We prototyped everything on an FPGA and used a sort of CPA-based leakage evaluation. We did this basically because it then makes it fairly easy to ask the specific question about the overwriting effect and not kind of get waylaid by other leakage effects, which are sort of out of scope for what we're doing. We're very focused on this particular effect. So, of course, mistakes can be made. This gives you some confidence, perhaps, but doesn't give you any guarantee. We also use the COCO toolset to do a more formal verification that there was no overwriting or no interaction between the values that were previously in one of these registers and the one that's overwritten. So I think in combination that we're therefore fairly confident that this is doing what it should be doing. Sort of efficiency-oriented evaluation is, well, in some ways not so interesting. In fact, in terms of the latency, the numbers here are, as you probably would expect. The latency-optimized version essentially is the same as the base core. That was the kind of intention. You don't pay any price for using these secure instructions in that case. The area optimization, because it's using this double step approach, essentially doubles the latency of all of these instructions. The area overheads are relatively significant. Whether this is sort of significant enough not to use it or to use it, I guess, is sort of debatable. IBEX is a relatively small core, so how this would look in comparison to a bigger sort of system, yeah, I guess you could sort of argue this. But you know, you pay a bigger price for the latency optimization, latency optimized version, and a smaller one for the area optimized version. Yeah, pretty sort of standard trade-off, really. Okay, so the takeaway points, I mean, I actually wanted to talk more about these a little bit than the techniques, than the design and implementation, because I think, like I say, what we're doing here is pretty straightforward in actual fact. I would definitely pitch this more as an exploration than a solution. It's not really clear whether there's plenty of other approaches that you could use to solve the same problem. It's not necessarily clear whether this is the best one, and in fact you have a choice between these two implementation strategies. You can kind of pick which sort of good and bad features you had. They're sort of complementary. So in that sense, it's sort of, yeah, we have now some more information about what the costs are. Whether they're palatable or not is a separate question. What, for me at least, in my opinion, is a bit more interested is some of the sort of bigger picture points that have come out of doing this sort of work. The first of which is this question of a more general leakage elimination hint. If you were to sort of expand this type of approach to other leakage effects, how do you actually write these hints in such a way that they are useful but not over-constraining? I think that's an interesting problem, but a difficult one to solve, and I think people will have very different opinions about what that could or should look like. One of the biggest challenges in doing something like this, and probably writing masked implementations more generally actually, is all of these extra core resources like memory that you don't necessarily have much insight into or control over. And I think really this hints at a bigger problem to do with the interface between the things, actually. So if it were the case that our memory had some signal by which we could say, look, we'd like you to kind of pre-zero this value or you know, and eliminate signal in some sense, then of course we could have much more robust guarantee about what we then end up with when we couple that to our core. Providing the IP vendor, you know, persuading the IP vendor to supply that type of thing is of course a bit of a challenge. But again, this feels like something that could be solved if there was an appetite to do it. And then the third and final thing really is to do with this issue of usability. I mentioned one of the usability problems for us was in the class 2 instructions, the load and stores, because the programmer has to actually be fairly intelligent about how they use these seed registers. I think usability in a general sense is something that's kind of overlooked when you sort of talk about work like this. And when you look at the raw numbers for the evaluation in terms of area overhead or latency overhead and things like this, I think I'd sort of kind of more comfortable with something that maybe is less optimal from that perspective, but is easier for people to use and actually allows them to write something more easily that ends up being secure at the end of the day. So I think usability in some way, shape or form should be factored into this type of stuff, but I don't really know how to do that. It's kind of a hard thing to quantify for sure. Yeah, I think that's it. Any questions?
Yes, so thank you very much. Any questions from the floor? Nothing. We have someone online, but no questions. So, okay, please.
That may be obvious, but of course you focused on overwriting leakage. You know very well that there are many other kind of leakages that can be as annoying, or I would even argue probably more annoying to deal with, like neighboring registers effect and all of that. That as a programmer are even harder to care about.
Mm-hmm.
Do you think that your approach could be extended towards handling this while leaving the same nice characteristic that you've shown in the conclusion in terms of usability and so on?
Yeah, it's a good question. I think, I mean, there's so many different effects that potentially could bite you. It's difficult to know where to draw a limit. So for sure, we're very conservative by just talking about one. I wouldn't want to say it any other way, that this alone isn't sufficient to solve the problem. Whether you have to use the same approach for every leakage effect, I think the answer there is probably no, because something like the neighbor effect, you can maybe solve inside the core by just having a different block. You don't have to communicate necessarily from software to hardware to solve that problem. So I guess it probably is more about using the right approach for the right effect and sort of, finding the covering set of all solutions that ends up with the best outcome. But it's a good question. I don't know how to approach some of those things, but it's an interesting thing to follow up on for sure.
But like, even given diversity of hardware countermeasure, do you think like the programmer could have a simple model and say, okay, this instruction has to be secure, and then the architecture would guarantee that the leakage of that is
I mean that's
like,
this is the dream, right? The ideal situation is you essentially just replace every XOR with a secure XOR, and then there's a robust guarantee that actually all of these effects aren't going to impact. And that for me would be the best case scenario from the programmer's perspective, because they just, it's trivial to use. You could teach a compiler to produce this, or you could just implement it with SED maybe or something like this. So yeah, that would be the dream, but I think the devil is in the detail here, and whether you can really achieve that, I think, is a bit debatable, especially when you consider if you really care about not impacting the latency, we couldn't think of a solution for memory access, for instance, that didn't have some usability issues. It's not quite as clean as just replacing one instruction type with another.
Thank you.
All right, yeah, thank you. So I have a few basic questions. So basically, any arithmetic instruction is going to write to a register. So do you have like secure versions of all arithmetic?
Yeah, this is maybe I maybe should have said this or maybe not, but it's kind of it's less expensive to essentially have any write into the register file follow this approach rather than turn it on and off. So basically, for free, you pretty much get this.
Yes, so you have a simple ALU which has a single path going to the register file and all of that.
Yeah, but so adding extra instructions is really the cost there is in terms of the encoding space more than the hardware implementation, I think.
Now, if this showed up on like RISC-V, then these guys would be automatically saying that, you know, our processors are high-end processors, they are all doing register renaming. It's kind of cool that this is generic, that one can kind of choose the implementation technique, but then they would also say that, you know, I have process switching, I have a stack, I have all of these other things. So this is kind of, I suppose the application area of this particular ISA is kind of limited to a microcontroller that is designed specifically to do masking. That's my guess.
Yeah. So I think it's fair to say we at least try to make sure that the approaches we're taking are generic. So this idea of having a kind of gadget to replace the registers, I think it's plausible you could apply that to larger designs. We are actually trying to do that. So we're working on the CVA6 core, which is, yeah, this is an application class. I mean, how much this costs is not going to be a pretty outcome for sure. But the reason for doing this isn't so much I think it's clear it is going to be costly, but the question is more about whether it really works out or whether there's any detail that you can't deal with.
If you're an application class, then every time there's a task switcher, all of the registers go into stack, and then you have to do a little kernel modification. But yeah, it might be doable. All right, so that's any other questions? All right, let's thank the speaker again. So that was the last talk of this session. Thank you all.